students. I know you're probably tired of the nervous system. I promise you this is the last chapter on the nervous system. Then we'll get into some of the good stuff. This one here, though, it's just our general and special senses. It's just telling how our brain deals with the surroundings and the inside of the body. Okay? All plasma membranes, they have receptors for chemical, electrical, mechanical. Plasma just means a cell wall. Okay, so we have our sensory. Sensory does what? It picks up the information, and then we notice that information, so we have now perceived it. Okay, that sensation goes up to our brain and it decides what to do with it. That's all. So general is, temperature, pain, touch, pressure, vibrations, just standard stuff. Special is going to be things, smell, taste, balance, hearing, vision. I won't say they're unique because everybody has it, but those are considered to be special senses. Now, each receptor means receptor specificity. It means it's only going to be receptive to one specific thing. Okay. Let me see. I don't know. A good example for receptor specificity would be, I can't really think of anything right now. But basically, it just means the receptor is only going to react to one thing. All right, it's just that simple. It's like you get used to, like your dog gets used to the sound of a treat bag being shaken. He hears that and he reacts to it. He knows exactly what it is. He's receptive to it. He doesn't notice or care when you actually go and you get a plastic bag. It doesn't have the same sound as the bag that his treats are in. So that's probably the best way I can do it. Free nerve endings just mean that they're ready to be stimulated. Now, receptive field, the best way to understand this is the neuron. Okay, so my little drawer. Okay, so here we go. We got the axon, myelination, comes right here, comes on out. Now here are the free nerve endings. Now, this is their field that they're specific to. This guy might be specific to touch. He might be specific to temperature, vibration. So this one right here is going to be specific to something else, but they all have their own field, right? Okay, interpretation of sensing means those neurons will be activated, so we know the location of the stimuli, and then we know the force of it, and the nature of the stimuli. Like if something's crawling on you, you can feel it on your hair, stuff like that. Tonic means that they're always working. Phasic means they come and go as needed. You're not going to have pressure receptors going all the time. It's only going to be activated when something pushes on it and you feel the pressure. That's phasic. Comes and goes. Your eyes, though, the photoreceptors, they're always going as long as your eyes are open. Okay, adaptation means that you feel something, you notice something, there's a stimulus is there, and then you just accept that it's there. So peripheral adaptation means that it's going to be things that are they're not in your central nervous system. Okay, it's just that simple. So touch receptors, things like that. The best example is always women. When first time you put on high heels, they killed you, but you thought they looked good. Everybody gave you attention, so you go running around your heels for a couple of hours. Your feet go numb. The next time, you get to where you can wear your heels more and more often. Eventually, you get to where you just don't even feel your feet, I guess, and high heels just become normal. Central adaptation. This one happens fairly rapidly. This is like the old barking dog. You hear it at first and it bothers you, but you can ignore it as long as you're talking to somebody else and doing stuff. Central adaptation means that you can block things out. If you think about it, it's like you're at a nightclub. You can talk to somebody with all the music and people and all that stuff around, but you can hear them because you blocked out everything else and you're focusing on that one person. See, I don't want to go into too much of this stuff. Okay, so external receptor means the external environment, not within your body. Proprioceptive is body position, balance, where we are within that exterior. And interior receptor is going to be inside your stomach. Like, when you get hungry, your belly starts to hurt. Nociceptors are pain. Thermal is temperature. Mechanical is pretty much movement, like something moving on you. and chemoreceptor is going to be chemicals. Mechanical receptor is going to be like in your ear, the stereocilia. Chemical is going to be nose and taste. Let's see, I don't worry about the general right there. Okay, so these are different kinds of pain. So we have our fast pain, which means you stepped on a tack. Slow pain is kind of like a chronic, just burning, just kind of delayed, bothersome pain. And referred pain means that we have something else is the problem, but the pain is going somewhere else. The most common is going to be the liver, gallbladder. Referred pain is going to be up into the right shoulder. We know a heart attack goes down the left arm. And of course, if you have kidney pain, it's going to run down the inguinal crease. And this thing right here, once your intestines go, everything just kind of starts to feel bad. Let's see. Thermoreceptors, don't worry about that. It tells you what it is. It's just temperature, mainly in muscles, skin. Mechanical receptors are going to be our tactile, touching. Baroreceptors are going to be pressure ones. We have baroreceptors in our carotid artery that recognize how strong our heartbeat is. We have baroreceptors in our intestines because they're hollow tubes. So when something puts a stretch on those, the baroreceptors get fired off and they push. We have peristalsis and we have a mass migrating movement. Proprioceptors, those kind of tell us where we are within. They're our balancers. They're like stretch receptors in our muscles. You see, fine touch and crude touch kind of tells you what it is. See, it's just easier to go in here. So what you be aware of is free nerve endings. They're very sensitive. The ones on our hair are very sensitive. These are all tactile. These are touch. But as we go down, you see, what I want you to be aware of is the Ruffini and the laminar. Once again, it's still like kind of light touch. The laminar is a little bit deeper touch. The bulbous corpuscle just tells you if there's a stretch, so your collagen fibers. This is what we try to play with, the bulbous corpuscles. When you get the athletic, the tape that sticks onto you that's supposed to help you with pain and everything, it's supposed to keep these guys at bay. And it's your laminar corpuscle. So these are kind of deeper in your skin, so this is for like harder touch, more firm. So baroreceptors I already told you about is in your hollow organs. They feel a stretch and they cause a reaction. You see, Golgi tendons, they're a stretch receptor that are actually in your tendons. You hit those, boom, things jump. See, chemical receptors tells you what the chemicals are. See, I'll go crazy on all this stuff. What I want to do is get into special senses. So, smell. Right here, cranial nerve number 1, up on top of the nose, free nerve endings. They smell the chemicals in whatever's coming in there, in our nose, and sends that information up into our brain. So it's just showing you we have chemicals that are hitting those nerve endings, and it stimulates this nerve, sends it on up, and it says this smell was this kind of sensation. And it kind of tells, you put all that stuff together and you smell a flower. You smell a fresh one from your cat in the litter box. All those things. Most smells aren't good in this world. Okay. I don't want to go too crazy on this. Okay. All you need to know is olfactory. We don't have the ability, we don't discriminate nearly as good as like dogs. We smell chocolate chip cookies. A dog will smell the chocolate, the flour, the sugar, the baking soda, whatever else you put in there, the nuts. Yeah. Okay. Gustation is just taste. And all this is, you can see we have these little lumpy bumps on our tongue, and this is our taste. So as we chew our food, we have chemicals from the food that are going to get in there and they're going to stimulate these receptors. And depending on which receptor and how often, it tells you how strong the taste is and what it is. Okay. This is what I want to get to. So, the parts of our tongue. Now remember, what it is that we taste, we'll go into the flavors. But it comes right up through, well, basically through the facial nerve and the glossopharyngeal. It comes up, goes up into the thalamus, the hypothalamus, and it decides what to do. And it'll send it over to the gustatory cortex. That's where we can kind of like make memories with it. But we also have the somatic, where think about what goes into us being able to chew so much food and not bite our tongue. We have to move the food to the back with our tongue and then bite down and keep chewing on stuff and not bite our tongue. We do every now and then, but it's amazing how little we do it, considering how little space there is in our mouth. Okay. Now, when we're born, we have a lot of taste buds. As we get older, we've used those up, which is why when people get older, they tend to like not really care what they eat. They tend to just be satisfied with whatever. And they lose their sense of smell as we get older too. It's not nearly as strong. Like anything, when you're young, you're all strong and everything works perfect. And these are our sensations when it comes to taste. Most plants that are poisonous are bitter. That's why it's hard to get kids to eat vegetables. Okay, equilibrium and hearing. All I want you to be aware of is that's going to be your cranial. That's going to be your cranial nerve number 8, your vestibulocochlear nerve. So we start off with first. Okay, so our external acoustic meatus is the outer ear. It's the ear you shove the Q-tip in and you twirl it around like your brain itches. Don't do that. But we do it. And what that does is that actually can push a bunch of wax up into this area, and then you have to go to a doctor and have the wax dug out. Doesn't feel good. Okay, what I want you to be aware of is sound comes in through your ear. It hits your tympanic membrane. It vibrates your tympanic membrane, which now vibrates your auditory ossicles. The first one that vibrates is going to be your malleus, or your mallet. And that's going to start hitting on your incus, or your anvil. Then that's going to reverberate and vibrate into what's called your stapes, or your stirrup, and that goes into your oval window. And inside here is your cochlear apparatus, where it is filled with a liquid, and it travels through that. Okay, and that is where hearing happens. So our external ear is up until our tympanic membrane, our eardrum. That's our external. Our middle ear is where our ossicles are, and here's our eustachian tube that drains to the nasal pharynx. And so this is our middle ear, and our inner ear is going to be inside of our temporal bone, and that's going to have the cochlear apparatus. Okay. Now the auditory tube, the eustachian tube, that's the thing that has to get equalized when you go up in a plane, when your ears pop. Let's see. Okay, it's just showing you it's in our temporal bone. Okay, I already took care of that stuff. So here we go, a little bit closer. It's your eardrum, but you can't call it your eardrum anymore. Now you have to call it your tympanic membrane. And this first one is going to be your malleus. And then that's going to shake, because as your voice makes the air vibrate, it makes this vibrate. Okay, so as this is vibrating, it's shaking up your malleus. So your malleus now is tapping down on your incus. Your incus now is taking that information, that vibration, and is putting it down onto your stapes, which now puts it into, well, it goes through the oval window into your cochlear apparatus, this area right up in here. Smallest bones in your body. You can look through the light, through an otoscope, and you can actually see these sometimes through the eardrum. Okay. Let me see. The best way to do this is really just to get in here and just show it to you. I'm not happy with the way the book actually shows this. Okay, here we go. So, we're now going to have the sound is going to travel in, it's going to hit the oval window, and now that sound is going to travel down into, it's a labyrinth, okay, so it kind of goes and it swirls around in here. So as it's swirling around in here, it's going to be taking these hairs and bending these hairs. these hairs that would be straight, they start to come up like this. They start to come up like this. They start to bend. Every time the hair bends, it sends off an impulse, a nerve impulse. Okay, now we have our perilymph and our endolymph. Endolymph is the blue, perilymph is around it. It just means liquid. Don't go carried away with it, okay? Let me see. This doesn't even talk about hearing. It goes more into equilibrium. Okay, it does go back to the hearing. Alright. It's just the gross anatomy so far. We don't need to go into too crazy with this. Okay, these guys right here, this is your semicircular canals. These are for balance. Okay? We have our utricle, these little bulges right here. Alright? And let me see. And then our macula is inside. A little deeper. More detail on that a little bit. Okay, this is what I want you to be aware of. In the ampulla, so the ampulla is right where before these canals go, the little bulge right there. So that's going to be your ampulla. In your ampulla, what you have is you have the endolymph. You have this fluid in here. And down in here we're actually going to have, this is where our nerves are, the basement membrane, nerves sticking through. These are the cilia. So as the cilia is sticking out, I want you to think about this. Every time you move your head real quick, it's like this, like a bottle of water. It sloshes. Okay, so that liquid's going to slosh. As that liquid sloshes, it creates a current. That current is almost like seaweed, like a kelp bed. Every time the ocean currents go, it bends these hairs. And when it bends those hairs, it kind of tells your brain how we just turned, how we moved. So it is responsible for dynamic movement. So these guys are dynamic movement. Okay, you see this guy right here? It just got bent. Body knows this got bent. It fired off an impulse down to this nerve. This knew exactly which one it got bent and how strong it got bent. So it knows what kind of movement was just done. Okay, it's just that simple. And these semicircular canals, all I want you to understand is they hit all the planes that we could possibly go in. Okay, all the movements we could possibly do. Now it's when it gets into our static. Our static is actually going to be, let me see, let's talk about static. Okay, the static is going to be in the utricle. Mainly about it is it has these little rocks on it. So our static balance is not dynamic, which means we're not moving. It's when we're kind of held still, sitting. It's what keeps us at the horizon. Okay? So these otoliths, what happens now, because they add to gravity. When you turn, when you put your head down, so then normally when your head's straight, they're just pushing down. Nothing's going on. But you look up, and what happens? These guys' gravity pulls them this way. So they slide downhill. They bend the cilia with them. And that tells your head, your brain how you just moved your head. Okay. So what I want you to be aware of, though, is this is the vestibular portion of cranial number 8, the vestibular cochlear. Okay. Now the cochlea, we already talked about all these different parts of the ear. But what about any of that stuff? Okay. So here's the organ of Corti. Organ of Corti is where we have the nerve fibers that come in. As you can see, they come up, and here is the little stereocilia sticking up. Okay. So this is what I want you to be aware of, is this is our hearing centers. So as the brain is, okay, as we have stimulation that comes in, we have the sound waves that come down, they're going to be vibrating on the endolymph, and they're going to be hitting from the perilymph, they're going to be vibrating, they're going to hit the organ of Corti, which is in the endolymph. It's going to stimulate those hairs. Every time those hairs bend, it's going to send out a nerve impulse, which travels down the cochlear apparatus, which then goes over to our temporal lobe, and we're going to process that as sound. Okay? We'll go into more detail on this in class. But just understand, the cochlear portion processes sound. Okay. Now, when it comes to our vision, palpebral just means eyelids. Eyelashes, we know what they do. Our eyelashes are for blinking. Lacrimal apparatus is for tears. So, what we have here is our lateral angle. Our lacrimal apparatus is up here. We make our tears, they come down and they wash our eye, the anterior portion of our eye. They come over into this side, which is the corner, okay? So the lacrimal caruncle, and they go into some of that is your nasal lacrimal duct, which then comes down, drains through the puncta, and it drains into the back of your nose. So here's your lacrimal gland. As you can see, it'll wash across your eye. You see the tarsal plates are just kind of like the harder portion that your muscle is going to attach to and pull it up. Okay, levator palpebrae muscle brings it up. Okay, so our eyelashes actually have some glands on them. The conjunctiva is the area that actually covers our eye. So that's where we have our nerve and our blood vessels. It's in the conjunctiva. Let's see. Okay. So a sty is pretty much just going to be one of your accessories. Could be in your eyelids. Okay. And all the angles. And here's your nasal lacrimal duct. That's going to drain your eye. See, lysosomes and all that. That's just enzymes to keep your eye nice and clean. Okay, so here's your anterior cavity. So this is going to be your lens. This is your iris. So the anterior cavity is everything in front of that. Everything behind the lens is going to be your posterior cavity. So light comes through this way. Light goes through your cornea, then it goes through the pupil. The pupil is inside of your iris, then it goes through your lens, and then it's going to focus, hopefully, on your macula, on your fovea centralis. Okay. So your sclera, which is the hard white part of your eyes, it changes and it becomes perfectly clear when it becomes your cornea. Then it goes back to being your sclera. When something's sclerotic, it means hard. So your sclera, the whites of your eyes, have a lot of protein. They're very, very tough. Okay. Now the vascular portion of your eyes, what I want you to be aware of is this portion right here that comes through. This cranial nerve number 2. As it comes in, this is going to have the nerve endings, and it has the blood supply that comes in and it feeds to your retina. So all of this is your posterior cavity, and it's filled with this vitreous thick fluid. Okay. Now, I need to get into more detail here. Okay, all you need to know about the iris is we have the pupillary sphincter muscles. There's little circle ones. They react to your sympathetic nervous system, makes it dilate. Parasympathetic, they kind of relax, go back. What light does is the brighter the light, the smaller it is. When it's really dark, it dilates to open it up. Okay. The choroid is just this area where we're going to have, let me see, where is it down here? Okay, so our ciliary muscles, they attach onto our lens and they pull. So the ciliary bodies are these guys right here where the muscles are. The ciliary zonal is where the ropes are that attach to the lens, and they pull the lens to make it more narrow. They relax it to get bigger. So the lens, what it does is it's going to focus the light rays perfectly on the retina. Okay. So the vascular area, we're going to have our choroid area, which is kind of like a space right up in here. Let me see if we can get a better picture. So here is your choroid layer. That's your vascular. So right up here is your sclera. So this is your sclera. Then we're going to have the choroid layer. And then we're going to have the retina sitting right there. And you know the retina, Our retina is red, so that's the reason why when you take a picture, it reflects the red lights back and everything else it tries to absorb. So inside of our eyes, on our retina, we're going to have our photoreceptors, which are our rods and our cones. Our rods are for night vision, our cones are for color vision. I want you to understand that aspect. Now, what happens is when the light rays come through, we're going to try to focus them perfectly on the retina. We want to get them right on the macula. So where is this? It's just showing you how the nerve fibers and all that stuff hit. This is where I want to get. This is what you need to know. Okay? So, the macula is this area right here where we have the best vision. So that's where we want to have the most light focus on there. Now, in the middle of the macula is going to be the fovea centralis. The fovea centralis is for color vision because the eyeball is going to be more narrow. So that's in less light. So it's going to be focused right there. As it gets darker and the iris starts to open up, the span of the light that's going to hit is going to expand too. But it's getting darker. So as it gets bigger and it focuses more away from the fovea centralis, we're now going to wind up having more and more rods because the rods are for night vision. Okay. Let's see. The anterior chamber is filled with something called aqueous humor, which means it's very watery. So from your iris all the way into your cornea, it's this clear liquid, very liquidy. In the back is vitreous humor, very thick. It's like a jello, clear jello, like jello. Vitreous, it kind of tells you what's going on. Okay. So this right here is your anterior cavity, anterior chamber filled with a liquidy fluid. Let's see. The vitreous, what the vitreous does, what's so important about the vitreous is by putting the pressure in the back, it keeps the retina along the walls, along the choroid, along the choroid. So it actually makes it so it's going to be nice and smooth because we don't want the retina to fold or it's going to get damaged. Glaucoma is when we have the aqueous humor doesn't drain very well, so it causes an increase in pressure, but that pressure can push into the back. Okay. So what happens now is when we get too much fluid, it starts to push on the retina, and the retina gets damaged, and that will cause damage. That'll even make you lose your eyesight. And we already talked about the lens, how it can change shape. I think we're actually pretty good. And we already talked about the optic chiasm. I'm not going crazy on this because we did it on the first one. So optic chiasm now, we're going to bring the visual fields together. Okay, that's all. Takes it back to the occiput, and that's where we're going to figure things out. I think we're good.